All right, let's get started today. So we're going to start Unit 12, getting down there. We're up there in the unit numbers. I don't know. Um, Nice to see everyone. I know some of you were busy weekends for competitions. I'm sure there are athletic going on, but there was also a coding competition going on and a 24-hour data analytics competition. So we had students from here at both of those. That's fun to see. So we're going to start with Unit 12, and we're going to do it a little differently this week. I want to have some time on Thursday for you to work on the project. I haven't released the project yet, but it's going to be more of an open-ended project that kind of gets you prepped for the final paper, which I also hope to have opened up by Thursday. So I'm going to have you start the learning activity and work through the learning notebook today after I do an introduction to this material. So we'll introduce the RAG model, and then we'll work through this notebook also. So let's start just talking about retrieval augmented generation here. So where this kind of fits in our levels is first we talked about large language models and just how to write better prompts, and what that is often called as prompt engineering for it. And then last week we did AI agents for this. So again, it was just writing prompts, but it was also coordinating multiple prompts and taking the output from one prompt and feeding it into another prompt. Chaining, we talked about lang chain, chaining prompts together for things. We also looked at Crew AI, where you could kind of specify a description for different agents that would be part of their prompt, and then give them a task, and then have them share information for when they did something, they could share that context with another agent as part of their prompt there. Both of those things work okay, but again, they tend to just use existing data or the existing LLM here. Now, sometimes with AI agents, you can search the internet. You can give them access to some tools like, a current internet search, as we looked at that. But it's still basically working with this agent a lot of times, or an existing LLM model. We're going to kind of continue on that, but we're going to add a whole new data retrieval system to an LLM. And this will let us use an LLM on kind of local data here. Often a company or an organization will have data that's not necessarily on the internet. Google hasn't looked at. So you can certainly ask an LLM to, describe the plot of a Harry Potter movie, or ask something about a specific book, or Alice in Wonderland or something like that. And there's lots of that on the internet, so the LLM will know about it. But the LLM doesn't really know much about like the St. Scholastica student handbook. Technically, it's probably been trained, it's probably seen the St. Scholastica student handbook once as it was looking at the internet, maybe. Or same with the St. Scholastica catalog, our course catalog there. So your LLM may not really know much about that here. But so what we can do is we can take our internal documents and feed those as part of our prompt to the LLM, so that we can get answers, have the LLM basically read our student handbook. Once we read the student handbook, once it has that in its mind, we can ask it questions about the student handbook here. We'll be doing the student handbook, but again, in any business, you could do an employee handbook, you could do your marketing material, you could do your social media thing, you could do anything. You could do all, if you're selling products, about a lot of instructions, booklets, anything like that, that your company would have, that you would want as a basis for querying, we can use those documents here. we're still not actually changing the LLMs in any way. We're not what we call fine tuning. We're not changing the weights, the parameters inside the LLM yet. Next week, we'll talk about fine tuning LLMs here, and that's where we have to retrain them. But here we're still using them as is, and that will help speed things up. So retrieval augmented generation's probably been the hottest, well, maybe not the hot, well, one of the hot things for the last 6 months in large language models and AI stuff. So all the companies have introductions to them out there, so we'll just go over a couple. There aren't great tutorials. Well, there's YouTube, but some of the tutorials we use, like from Google or Microsoft Learn or whatever, though a lot of those places haven't yet generated good multi-stage tutorials on this. So with the Explore activities, I'm still struggling to find some more. I'll try to, before Thursday, find some more tutorial-like things you can do with this. But the companies have their basics. So like IBM has what is augmented generation here, and walks through this. They also have a nice video talking about that. I'm just going to play that. Let's see, where am I with sound? I had some sound problem last time.
They get some things amazing right, and other things very interesting.
Okay, I'm going to turn it up just a little. I think. Turn this up and this down.
Alexi. I am a senior research scientist here at IBM Research, and I want to tell you about a framework to help large language models be more accurate and more up to date. Retrieval augmented generation, or RAG. Let's just talk about the generation part for a minute. So forget the retrieval augmented. So generation, this refers to large language models, or LLMs, that generate text in response to the user query referred as a prompt. These models can have some undesirable behavior. I want to tell you an anecdote to illustrate this. So my kids, they recently asked me this question. In our solar system, what planet has the most moons? And my response was, oh, that's really great that you're asking this question. I love space when I was your age. Of course, that was like 80 years ago. But I know I read an article, and the article said that it was Jupiter and 88 moons. So that's the answer. Now, actually, there's a couple of these following my answer. First of all, I have no source to support what I'm saying. So even though I confidently said, that article, I knew the answer, I'm not forcing it. I'm giving the answer off the top of my head.
This bothers my wife a lot. People ask me questions and I just give answers off the top of my head, and she thinks they should be correct and they should be sourced, and she just laughs at me for giving these answers. I like this part of this, that she just gave an answer off the top of the head. Jupiter, 88 moons. Everyone knows that.
And also, I actually haven't kept up with this for a while, and my answer is out of date. So we have two problems here. One is no source, and the second problem is that I am out of date. And these, in fact, are two behaviors that are often observed as problematic when interacting with large language models. They're LLM challenges. Now, what would happen if I had taken a beat and first gone and looked up the answer on a reputable source, like NASA? Then I would have been able to say, okay, so the answer is Saturn with 146 moons, and in fact, this keeps changing because scientists keep on discovering more and more moons. So I have now grounded my answer in something more believable. I have not hallucinated or got the answer by relating personal information about how old the moon is and how old the thing. All right, what does this have to do with large language models? Well, how would a large language model answer this question? So let's say that I have a user asking this question about moons. A large language model would confidently say, okay, I have been trained at what I know in my parameters during my training. The answer is Jupiter. the answer is wrong, but, you know, we don't know. They are not very confident in what answer. Now, what happens when you add this retrieval augmented part here? What does that mean? That means that now, instead of just relying on what the LLM knows, we are adding a context store. This could be open like the internet. This could be closed, like some collection of documents, collection of policies, whatever. The point though now is that the LLM first goes across to the content store and says, hey, you retrieve from me information that is relevant to what the user's query is. And now, with this retrieval augmented answer, not good anymore. We know that it is that. What does this look like? Well, first, user prompts the LLM with their question. It says, this is what my question is. And originally, it was just copied to the generative model. The generative model said, oh, okay, I know this response. Here it is, there's my response. But now, using the RAM framework, the generative model actually has an instruction that says, no, first, go and retrieve relevant content. Combine that with the user's question, and only then generate the answer. So the prompt now has three parts. The instruction to pay attention to the retrieved content, together with the user's question, now give a response, and in fact, now you can give evidence for why your response was what it was. So now hopefully you can see, how does RAG help the two LLM challenges that I had mentioned before? So first of all, I'll start with the out-of-date part. Now, instead of having to retrieve your model, getting information comes up like, hey, we found some more moons. Now, could you put it again? Maybe we can Saturn again in the future. All you have to do is you augment your data with information, updated information. So now the next time that the user comes and asks a question, we're ready. We just go ahead and retrieve those updated information. The second source. Well, the large language model is now being instructed to pay attention to primary source data before giving its response. And in fact, now being able to give evidence. This makes it less likely to hallucinate, to delete data, because it's less likely to rely only on information that occurred during training. It also allows us to get the model to have a behavior that can be very positive, which is knowing when to say, I don't know. If the user's question cannot be reliably answered based on the data store, the model should say, I don't know, instead of making up something that is believable and may mislead the user. This can have a negative effect as well, though, because if the retriever is not sufficiently good to give the large language model the best, most high quality grounding information, then maybe the user's query that is answerable doesn't get an answer. So this is actually why lots of folks, including many of us here at IBM, are working the problem on both sides. We are
okay. So that kind of gives you a basic kind of intro. We're adding data, augmenting our LLM with some external data source that we'll be bringing in here, and we'll look at some ways of doing that. So let's look at NVIDIA. And NVIDIA, they have this whole article about this stuff. But I really just want to jump into this diagram. Oh, I miss Ask Jeeves. Do any of you remember Ask Jeeves? That was like the internet before. You don't even remember the internet before Google. Never mind. Okay. Okay, let's go down here to this, not this model. This is the one we want to hope. Here. So here's our kind of our framework, a different picture of what we saw in the video. We have our large language model. Where again, we're feeding it a question. We have some chat history probably there, and we get out a question. But from that question, we're going to send it to what we call a vector store, a data storage of documents, basically. And again, maybe this will be just like, you know, the student handbook or the catalog, or maybe your marketing material, or your accounting, or your financial reports for your company, or something like that. So we have this storage of documents that we call a vector store here. And we're going to search through that and retrieve the documents that look like they might relate to this question. So we're going to get a couple documents. I'm saying documents, and that's not exactly right, but we'll say that for now. I'm grabbing a couple documents out of this, and I'm going to feed that and go back to my LLM with my original question and these documents, and then tell the LLM, okay, using these documents, answer this question, and it will give me an answer. So that's what we're going to be setting up today, is this sort of RAG model. And again, why it's called RAG is it's not just generating answer, it's retrieval augmented. We're retrieving some documents and inserting them into our query for this to work. So that's NVIDIA's help here. Now, Oracle, similar sort of they have another what is retrieval augmented generation here. And explains through key takeaways. So I like this description, but I'm just going to focus on one part of this is what are the benefits of this? And I kind of went over that video a little bit. Your RAG model has access to information that would be fresher than data that LLM was trained on. And again, it's easier to update your vector store, your database of documents. You can just add more documents to this or updated documents to this here. Again, your knowledge repository or vector store can be continually updated without significant costs. Next week, we'll look at retraining, fine-tuning a LLM. And that is just going to be a pain because I still haven't figured out how we're going to do that. Because these computers here and even our Google Cloud computers really can't do it within the week that we have. So we'll probably not actually be able to do that because we probably don't have enough computer power to do that. But just adding documents to our data store, that's not going to cost us much as far as computing power and stuff like that. So it can have more specific data to your company. They call this contextual data for this. And then we can also identify sources. We're not actually going to do that today, but a lot of these RAGs models will show us not only the answer, but will cite the source where this data was from for us. Here. One thing that was kind of implied here, but not, is that it will let us access or ask questions on LLM with proprietary data. A lot of companies can't use and post stuff to OpenAI's ChatGPT because they're restricted with sharing proprietary information with companies like that. So, if you're a hospital and you have a patient's medical record and you want to ask AI, look through this medical record and help me with the diagnosis of that. You can't push that out to ChatGPT because medical records are private and you would get into big trouble for that because, again, that would go into OpenAI's maybe training model. And then later on, someone could just ask, who suffered from this condition? And might know, we give a patient's name or something like that. So, but if we have that locally and run everything local here, then the data is never shared outside of our company. So if you talk to hospitals or banks, financial institutions, even companies that have a lot of private marketing or, financial information, they'll use RAG to do that because they can then have a previously trained LLM, but then just have it look through their documents here or their, patient records or their financial reports or something like that. Okay, so we've done IBM, we've done NVIDIA, we did Oracle. The last one we're going to talk to is Amazon. And again, they have their nice little introduction to RAG here. And they have a picture that's a little different, but similar, I think. So again, Here's our LLM here. We send a prompt to that. That's step one. We take that and we form a query to our retrieval system. And we have some, they call it knowledge sources, some documents or storage over here. And we get some relative information back. And so 3 is just sending that context, that relevant documents back. And now we're generating a new query, which is our prompt, plus this enhanced context, the information we got from our data, send that to our large language model, and that replies with a response back to us. So this is our kind of RAG system here that kind of coordinates things before it intercepts the prompt and does some stuff, gets some more data, adds that to the prompt, then sends it to the large language model for it. So that's, again, same sort of idea, just a different view of it here. Now, this has some notebooks. I just wanted to talk to you a little bit about these notebooks. And so we've been doing this in Google Colab with some Python libraries, and I've been trying to use Python libraries that are pretty widely used out there and examples that are pretty widely used. And the hope is that you could then use these in other places. So we've been using Google Colab. Amazon, AWS, their cloud system has similar stuff. They call their notebooks SageMaker for this. And so they have these different SageMaker notebooks here. And we can look at these for this. And my hope is that these won't be, that you could maybe understand these at this point. Now, we don't use Amazon because the setup to get this set up is a little complicated for you as a student here, where I can just do, since you already have a Google account, it's easier. So the main reason I don't use it is just to get your access and set up. You can, I mean, I have this set up for myself, and you can set this up. It's just not, it's not obvious. But here's the notebook here. We do some installs. We import some libraries here. And so again, this should look very much like our notebooks are going, you know, what we're going to look at today. This will look very bit. Now, some of the libraries are going to be different. So they're bringing in some SageMaker stuff, but they're also bringing in LangChain here for this stuff. Then they talk about deploying this, and this is cloud stuff, so we don't have to worry. We don't do that, it's a little bit beyond what we need to do. And then they're going to create a model and ask an LLM a question here. Now, some of these notebooks are going to use what are called Python functions to set this up, and we haven't talked too much about Python functions. I've tried not to use them too much, because if you're a coder, you're used to probably using functions and thinking this way. But if you're not coding, I think this makes it a little more complicated for this. But again, here's our variable for the question and our response. And again, they create different versions of it. And here's another version of this. Again, we're installing some stuff here. We're in something called Pinecone, which we'll see today. We're using Hugging Face and Hugging Face models here. And here we're creating a model here with Hugging Face's LLM model or Llama model for this. We're creating a prompt. We're putting it in and we're sending it to our stuff getting answers. So again, I'm not sure if you can, but my hope is that after this class, you know, you have seen some of this so that you can look at some of these other notebooks or examples out here and at least walk through tutorials and understand, you know, have a basic context for those here. So that's what Amazon has, is a number of these sample notebooks for doing these RAG functions. We're not going to use them exactly because, again, they have some Amazon SageMaker specific stuff in them, but a lot of, I would say, 80% of them are exactly what, or similar to what we do. So, okay, so let's do this. So, I'm going to go to Learning Notebook 12 here and open it up here. Now, when I open it up the first time, I'm not sure, it brings up this weird view now. I'm not quite sure why. I've updated the link, and again, there's been a week and a half ago, there was an update to an underlying update to Brightspace, which changed a lot of ways links have. So I'm still kind of working through this, but so you might see this. If this is the case, still say open with, just click on open with Google Colab up here. Open with Colab. So this is just the preview of it, basically. If you say open with Colab, it'll bring up this view, which is what you want for this. So you probably watch tutorials on YouTube or just things on YouTube like the Eclipse live feed, Iowa basketball, things like that. My Fridays are spent watching YouTube videos on AI tutorials there. So I watch a lot of these. So this is, and so this one I liked here. So we are going to be kind of following right along with, this is a producer called Underfitted. And he produces a number of really good AI videos here. And so this is walking through, and I like this example because he just doesn't, he's pretty good at explaining this and setting this up and working with this and explaining some of the underlying technologies or stuff of this. So I strongly suggest you watch this video. It's only an hour and 12 minutes there, but we're going to work through this here. But if you want some time to watch this video or not. Now, this person also, this provider also has a GitHub repository. So GitHub is where we store source code and has source code here. And he has a notebook here that he's created. And I've taken that notebook and modified it. It doesn't exactly run the way doesn't run in a notebook necessarily so well and doesn't fit what we've been doing in our class exactly, but it's close. So this Learning Practice 12 is almost, as close as I can get to his notebook and what he's doing in this stuff. So that's what we're going to walk through. Now in he's a YouTuber. We're going to prompt for a question and we need to have some documents. So he's going to take a YouTube video, generate a transcript from it, and then ask questions of that transcript. Now we're going to change this. So we're not going to use a YouTube video and we're not going to use a transcript. Instead, we're going to use the student handbook or the catalog or one of the documents from St. Scholastica here and ask questions of that. So that's your job, is to go through this tutorial, replace the YouTube stuff and this transcript stuff with a St. Scholastica document. So you can go through now, and again, you're going to have to do the write-up here also. So the first section is doing some installs, and he loaded in some libraries here kind of. And again, we're using a slightly different model for this. And again, we don't need a YouTube library. So I've just replaced his code with our code we'll be using with my OpenAI key and some of these and our other stuff. And right now our model is just gonna be GPT 3.5 for our model. Now, I've been using a variable LLM for our model. He uses a variable called model as his model. So again, we're just setting up both variables. So either one will work. Now, once we have this model, this LLM created, we can just ask its questions here. I forgot I ran that. I forgot to run this. And then I can run this question. So I say model.invoke to ask it a question, and I can give it a question and see how it responds. And again, just walks you through basic prompting here, and then does LangChain. And again, we did LangChain last week, so kind of does a good review of LangChain. So again, this is our basic thing. We just send a query to our model, get a response, and the parser will just display that a little nicer in some ways. So right now, this is the response. A parser would just maybe pull the actual answer from this and ignore some of the other stuff we get when we invoke this stuff. So in order to do all this, we use LangChain, and we have a parser. And so now when we run it, we get a better response here. Los Angeles Dodgers won the 220 World Series during the pandemic, where this answer was a little messier. It told us things about tokens and what model we're using and things like that. So again, brings up this idea of chaining these things together. We're gonna do a prompt template. I don't know if you remember when we did LangChain, we put in these contexts, these variables in here, and then we could say, here's a prompt, and then we could say, here's the context, and here's the question for this. And we could run these stuff and get an answer. And again, we could feed this to, we have a prompt, we send that to a model, and then we send that to a parser here, and then we can invoke this whole chain here. So again, this just kind of walks you through the basics of, oops, I have to define my prompt up here. So we define our prompt, and then we send that. So from our chain is, we start with our prompt, we send that to our model variable, and we send that to our parser, which again, kind of strips out the useless or the stuff we don't need in the response and just shows the text here. And then we invoke that chain. So with your questions, I just want you to look at some of these sample examples here. There's a number of sample prompts and stuff. Select one, or select one, and then write a sentence describing what that is. Another one, put a sentence as another one, and put a sentence here describing what it is for this. So again, here's where we're at, and then we build, combine some chains together for this. And this kind of getting to where we want, because we want to build these chains and we want to bring in data, some extra data to feed into this chain. So we have our prompt going to our model, we come out from the processor, we get some answers, and then we do something with that answer and feed it back into the model again and a parser. So here they're going to switch this, the response from English to Spanish here. So we have a translation chain we're adding in here for this in the context. And again, the video does, I'm not going to spend too much time on this basic stuff because we've already covered LangChain, but again, if you want, this video walks through this quite a bit and talks about it. So you can see it there. Okay, and again, to get this to work, I have to make sure I run, I have to set up these variables. So I need my translation prompt because that's part of my chain here that I need. So I'm feeding in my initial prompt with my here, sending it to a translation prompt, sending it to the large language model, and then sending it to a parser. Now you see these little vertical lines. These are what are called, well, I call them pipes. I don't know if that's old or not, but that is just a way of sending the output of one thing as input to the next thing here. Some places you may think of that is a OR, but ORs are usually two vertical lines. If it's a single vertical line, it's usually a pipe. So what this, and again, let's go a simple one up here. see these vertical lines? That just says, take the prompt and the output of the prompt is going to be piped into the model, and the output of the model is going to be piped into the parser. So those vertical lines are just basically, I often think of them like is connections of you know, cables or something like this. This just forms a way of connecting one output with one input here. And we can connect those together with LangChain. So again, I think a lot of this is kind of review. Not that you remembered LangChain from last week. You probably don't remember that at all. But again, it's stuff we covered last week. Okay, so, and that's why I want you just to do some summaries of it. Now we're going to take a full document, feed it into it here. So one of the ways we first started doing this is we could say, well, we're going to take the whole student handbook, feed that and give that to the large language model, and with a prompt, with a question, have it get the results. And that is going to fail because the document's going to be too big here. I'll just warn you, when you research stuff, some people are saying RAG and this whole model is now dead because large language models, the newer ones like ChatGPT-4 or Gemini, the amount of information you feed, it used to be like 2,000 tokens. So that's 2,000 word document maybe. And then they put it up to 16,000 words. That's a pretty big document. If you ever wrote, have you written a 5,000 word paper? That's, you know, a 16,000 word paper. That's a pretty big paper here. But now they are often at like 100,000 tokens. So now people are wondering, isn't it just, can't we just send the whole document here? And but there's arguments back and forth. But again, with existing models and stuff, this is going to fail. So we're going to try to send the whole document. Now, he had to get a transcript from a YouTube video and uses a library called Whisper to listen in and transcribe a YouTube document here. I put this all in code. We're not going to do this here. Instead, you're going to upload a document here for this. So we're going to try to choose one of these documents here for this. But we've got to upload a document. So if I look over here in the folders on the left, there aren't any documents. Now, if these were in your Google Drive, and I could do this, you can mount your Google Drive in here, and anything in your Google Drive you can load up here by connecting up to your Google Drive. And it's in my Google Drive, but I can't figure out how to have you connect up to my Google Drive easily. So they are on Google Drive, but I can't have you necessarily mount them right here easily. So instead, we've got to do this where I'm going to have you download the documents and upload them. And I don't mind that because you might have some documents on your computer you just want to upload anyway. So I'm going to show you how to do that. So first, we're going to go to the Google Drive folder. And I'm going to do the student handbook, I think. So I'm going to click on the student handbook and download that. And now there's two different formats here, PDF and text. I'm going to show you the PDF of the catalog. There's our president, there's Barbara. And again, nice format and stuff. PDF, well, you know, printer ready, but not necessarily LLM friendly. Here's the catalog text here. It is just the words of it. And that is a little more friendly to our LLMs. So we're not going to grab the PDF of the student handbook. I'm going to grab the text version of that. Now, how do you, if you don't have a text version of a document, how do you get one? So some of these I can just open up and save them. I can open them up like in Adobe or something and save it as text. Some of these you can just open them up and copy out, highlight the text, copy and paste them into a text editor like Notepad or something like that, and get the text out of it. If you're in Microsoft Word, you can just say save as text or stuff. Okay, so I've downloaded this file for this. Now I'm going to go back to this, my notebook. I'm going to hit this little upload button. So there's this little arrow up button in the left corner. I'm going to click on that and find my handbook in downloads here and say, open that up. And it says, you know, that you've uploaded it, but as soon as your notebook goes away, your data is going to go away, and that's fine. So it's brought it up here. So now I'm going to change my documents here. I'm going to get rid of these. Well, I'm just going to comment out these first couple. And I'm going to put in my document name. So mine is called student underscore handbook. I'm going to read that in, and if I click this run, it should start displaying the student handbook with the instructions. So the first thing is code of conduct, then the library policy, and that sort of stuff. So see if you see that. Now, if you get an error, for example, if the file not found, I'll get this error, file not found error. So it's maybe you don't have the file there. So again, remember, we're clicked on this Tom's Drive. In here, we downloaded one of these documents. So like, here's the catalog. I'm going to click on download to download it. Or if I double click on it, I can say download up here too. So somewhere or other you have to download it. And then go back here and upload it. I mean, again, I've opened up this little folder icon on the left. And then I'm going to hit the upload button and click. I'm going to do the catalog this time. And it should be there. And now, then in here, I want to make sure this is spelled exactly right, not handbook. It has to be exactly as it's spelled over here, and I run it, and it should display that. So see if you can get that data displayed. So back here in your write-up, it's going to ask you a couple things. The tutorial data, this is this data up here, and ask you to describe this here. And again, what is this doing? It is trying to get a transcript of a YouTube video. So it's going to first check if the transcript exists. If not, it's going to use a YouTube library to get this YouTube video. It's going to get the audio file from it. It uses a library called Whisper. And with Whisper, it's going to try to transcribe that video. So I'm not going to go over what it's doing here, going through the audio files, and each one it's using Whisper to try to create a transcript of that. So basically all you need to write down is it's using the Whisper library to create a transcript of a YouTube video. That's what it's trying to do. And then you're going to use one of the documents that's available here, and then we're going to load that in here. So I ended up using the student handbook here, but you could use the course catalog or anything. Now we're going to try this. We're going to send the document to the language model, and we're going to ask it a question here. And this question is actually from the video, so I'm going to actually change this to be a question, or I could, that would be in the student handbook. Like, my question might be, are students allowed to drink alcohol in their rooms there? Or what is the policy, who can use the wellness center there, or some question that's in the handbook here. I'm feeding this in here, and I should get an error anytime now, because again, it's trying to send the entire student handbook to ChatGPT and asking a question based on that student handbook. And I get this error message: the model's maximum context length is 16,000 tokens here. And your message is 44,000 or 41,000 tokens here. So my thing is just too big that I'm sending in here. So it's 41,000 words-ish. Again, token is not necessarily a word, but it's proximate in the same way that a meter is about a yard sort of stuff. Here. Okay, so this is going to fail because our model is just too big. I mean, our document is too big. So then we go on to 3. We're going to split the document up into parts here and feed just one of those parts into our model for this. So we're going to run this. We're going to load this. And again, LangChain there are lots of different libraries, but we're going to mainly use these LangChain models here. So again, we're going to load in this text document and just show it. So this is actually what the model looks like here. And then we're going to run it through a text splitter. There's lots of different ways of splitting here, but in this example, he splits it into chunks of 100 words, 100 tokens, and there's a 20 token overlap for this stuff. So that's what this talks. Describe how the document is split into chunks. What size chunks is the document split into, and how many chunks are there here? Now, 100 characters. So what we're going to do is try to find segments and send that to the language model from our handbook. And basically, if I look at our handbook, I'm going to select like 100 characters. So I might, and they're going to be kind of randomly selected. So I might just select this 100 characters. Is that 100 characters? Maybe. That's not a very big section here, and it misses a lot of context. I don't even know what section that's in here. So 100 characters probably is too small for it. If we had smart selection where we are selecting each paragraph, that would be good, but I'm not. I'm just randomly saying I'm going to start here and select 100 tokens. And then I'm going to overlap 20 tokens and select the next 100 tokens for that. So I'm actually, so 100 is probably not going to be very good. So for us, we're going to switch this to 1,000 characters. So we're going to do a text splitter where we're going to do a chunk size of 1,000 and overlap. There's doing an overlap at 20. If you have 1,000, I don't think 20 is great. I'm going to change this to 100 just for myself. I think that's a better, but you can leave it at 20, the default there. But again, that's what we're going to do is just run this text splitter with chunks of 1,000 for this. So it breaks our document up into lots of parts. Oh, yeah, let's talk about embeddings here. I'm wondering if I can find his discussion on embeddings. We have his. Okay, let's see if I can play. He has a pretty good description.
So we have
Oh,
just smaller documents, and each one of those documents will fit the context, which is good, right? We don't need to send the transcript. And the problem, however, is that we need to understand which of those documents to send to the model. Like, we get a question about artificial intelligence, how do we know which of those smaller 1,000 word documents are the ones that we need to combine and send to the model? That is the question that we need to answer next. And this is one of the most fascinating topics working with large language models, working on this type of systems that you are going to find. And it's the idea of embeddings. Okay, so let me show you first what this looks like here. Okay, and you're gonna have to trust me for 1 second. Then I'm gonna make this a little bit more clear. So this is my proposal. So we start with the transcript, and we split it into documents. We really did that, and we have all of those smaller documents. Imagine that there is a magic formula for us to compare a question with all of those documents. And that magic formula that I'm calling computing similarity here, that magic formula will tell us which of those smaller documents are the most similar to the question that the user asked. And using that similarity, we could return the documents that are the most similar. So we can select the documents that we want to send as context to the model. So the process of doing that, I'm saying this magic formula, which actually exists, we can generate embeddings for every one of those documents and generate embeddings for the question. Now, what an embedding is just a vector. In space, you can think of coordinates in a multi-dimension space of where a specific idea is located. Okay, so here's the way it works. Imagine that I talk about books. Grab the book. So it's deep learning with Python book from already. I'm talking about books, and I generate the location, this multi-dimensional space, where you would put this book. That book will be here, this location here. I don't know, say it with a hard problem again. But imagine, actually, let me just put this here. Let's say I locate this book, that corner over there. Okay, that is the coordinates where this book is going to be located as a concept in my world. And now I grab a can. Okay, I grab a can, and this is a very different concept. So it's not going to go close to the book, it's probably going to go to a different corner of my book. So the coordinates representing this can are going to go somewhere else. And now I'm going to grab another, this is a human in the loop book. This is a very similar concept of this book. So if I were to locate, if I were to generate coordinates for this book, those coordinates would probably place these two books very close to each other over that corner, and very far apart from the can that's located on that. So,
okay. So he goes over and talks about that, but the idea of these embeddings is that we are going to take these text documents and create a multi-dimensional vector, a bunch of numbers to represent them. And we did kind of embeddings a while ago where we had some concepts. I said, you know, one of the dimensionalities might be how colorful this is, and we tried to take words and assign them to a sequence of numbers there. So how playful is this word, or how colorful, or how tasty is this word? And we tried to do it with ourselves, and then we talked about the computer creates its own embeddings to optimize things there. So this is the embedding. So we're going to run this. What it'll do is create an embeddings for this document. Now, It was just a mapping of these documents, and you could imagine it like in a library using like the Dewey Decimal System. Do you know what the Dewey Decimal? I mean, you used a library. You still taught that in school, right? So, a library Dewey Decimal System. You have some code in the library. You know where it is in the library, but you may not, if you've ever been to the Library of Congress does not use the Dewey Decimal System, it used the Library of Congress numbering system. So if you have a book at the Library of Congress and it has a Dewey Decimal number on it, it doesn't help you at all at the Library of Congress because it's a different numbering system. Same here, we have to, if our language model, and again, our language model is going to embed our question and send it into the language model. But if we want our documents to be embedded, we have to use the same model as this. So if we're using OpenAI for our stuff, or as our language model, we have to use our OpenAI embedding here. So that's what we're doing here, is we're creating this OpenAI embedding. So we're just embedding this phrase, who is Mary's sister? We're embedding that into an embedding, and it is a vector of 1,536 numbers. And here's the first couple of them. So it has 1,500 dimensions, different numbers representing, like in my mind, I'm always thinking of, oh, this is how tasteful or tasty it is, and this is how energetic it is, and this is how colorful this phrase is, and this how much it has to do with family, or this how much has to do with this. So there's all these dimensions. Again, the computer doesn't have things like that, but it has found dimensions to encode this word or this phrase here. So we can encode whole phrases, whole sentences, whole documents, that sort of stuff here. So again, we're encoding that. And now here's an illustration of that. We're going to encode two different sentences here. Sentence 1 and sentence 2. Mary's sister is Susanna and Pedro's mother is a teacher. And then we're going to compare those here with something called cosine similarity. Oh, DeVito, he gets so excited about cosine similarity. I don't know how many cosine similarity videos you watch, but you should definitely sometime Google cosine similarity in YouTube and watch some videos and find someone who's excited about cosine similarity versus some of those other similarity methods, because everyone knows cosine similarity is much better than those other ones. Okay, so I'll just suggest you do that sometime. Okay, so cosine similarity is, we're going to see how similar our sentence is to these two sentences. So our sentence is, who is Mary's sister? Now, is that closer to this one, Mary's sister is Susanna, or this one, Pedro's mother is a teacher? Which one should it be closer to? Well, it has some similar words in here for this, and it also has sister, Mary, so it should be similar, more similar to this, and it doesn't have to have the same words. Sometimes it could just have the same ideas here. So cosine similarity, it says it is 91, the distance to the first sentence is 91, or the similarity measure is 91, not the distance. So it is, and we want this higher. If closer to 1, it is very similar. So, and then the similarity, the other one is 76. So it is closer to this one than to this one here. And so if we're going to use, want to answer this question, and we should, just deleted that. There. We should be using this data and not this data for that. So that's what this is doing here. So that's what this is asking to you. Describe documents split in trust, what type of encoding is used. Again, we have to use the OpenAI encoding. How many models did that have? That had, the length of the embedding was 1,536 numbers. The vector was that big. And what is cosine similarity and why is it used? Why do we need a similarity measure? So again, we need to measure how these things are similar to each other. And cosine similarity, it is just a measure of the angle apart. I don't know if you remember cosine, but again, it's just a measure of if, again, he was doing this room here, and if two things are in the same corner of the room, they have the angle between them is very small. Well, if they're in different corners of the room, the angle is going to be bigger. And basically, it's a measure of that angle there. But it's set up so that the more similar it is, the larger, the closer to 1 this will be. Because I don't know if you remember cosine, but a cosine of a really small angle is 1, and the cosine of a big angle is 0. There, that's how cosine works for this. Okay, so that's what this cosine similarity, and you can click on this link, I think, to tell you all about cosine. Oh, I don't like the Wikipedia articles. Oh well, it's okay. Okay, so once we have that set up, we need to actually store this stuff somewhere. And we're no longer storing documents, we're storing these embeddings. And these embeddings are what we call vectors. These are arrays of numbers. So every document basically is an array of numbers, or has like an index, a code embedding for that, this array of numbers. So we need to use what is called a vector store here. So a vector store, we take all of our documents, create embeddings for them, and put them all in this vector store. Then we can take a question, send it to the vector store and say, give me all the similar embedded documents here. And it will use cosine similarity to find the documents that are similar to the question we asked. So the first thing, we're going to create a really simple one to try out here. So again, we're going to create this embedding with 6 sentences. Mary's sister is Susanna. John and Tommy are brothers. Patricia likes white cars. Pedro's mother is a teacher. Lucia drives an Audi, and Mary has 2 siblings. So some of these things have talks about cars. Some of them talks about brothers and sisters and siblings. So they should be stored in different locations. So if we look at this stuff and we look at an answer like this, I'm going to actually kick this up. Rather than k equals 3, I'm going to set this up to k equals 5, I think. Display a couple more. Okay. So if I have a query like who is Mary's sister? The most similar one vector in my vector store is Mary's sister is Susanna, because I got similar words in here. The next one is Mary has 2 siblings. Both of one's 91% match and one's 90% match. That's not really percentages, but similar. What doesn't match? Lucia drives an Audi. That's only a 75% match. It's still talking about people here. So it's in people's motivation. So it's not talking about, tigers or some weird, so it is somewhat similar still, but not near as similar as these. So again, our vector store, we can give it any phrase and it'll find the other phrases that are similar, and it'll give us as many as we want. We can say k equals 5 or whatever, just rank them by how similar these are. So again, in order to link this in, we need to tie this into what we call retriever, goes to our vector store, gets our data, and sends it on. So we create a retriever for this, and we can run this. We can add this into our system. So our question here might be, what color is Patricia's car? We can run this in our chain here, and it'll return white for that. So it's going to be looking at our through our document store, which is just 6 sentences here, And one of them is Patricia likes white cars. And so if we ask it what color is Patricia's car, it's going to say white. Or if we ask it what car does Lucia drive, it'll say that. Lucia drives an Audi. So again, this just is a sample one with these sentences. We're going to replace these sentences with actual documents or sections of the student handbook. So remember we read in the student handbook above here. Where was it? We read in the student handbook here into our document. So I have my document. We then split the up into a bunch of parts here. So we split it up into a whole bunch of parts with our text splitter. And now we're going to feed that into our database. So we're going to load the documents into a vector store. So here's our documents. Those are all our split up documents. And we've also created embeddings for all of them. Did I create embeddings? Yeah, we must have created embeddings above for them. So we created embeddings for them. We're going to do that. That's going to take a while to load it into the document store. Then we're going to create a new chain here where we're going to ask questions of our model. So I think I loaded the student handbook in. So I think I'm going to do this question. Can students drink alcohol in their dorm rooms? Based on the information provided, students of legal age are allowed to use alcoholic beverages in private rooms of student apartments. However, the college reserves the right to determine if the alcohol use is excessive or violates their values. Additionally, summer hall residents hall is specifically an alcohol-free building and its residents and guests regardless of age. Sounds like it's quoting the student handbook pretty well. Here. Now I can ask it some other questions. Like here, this is a question that I would think isn't in the student handbook, but is in the catalog. What courses are required for the history major? Let's see if it makes up an answer or not. And this is one of the nice things about these things that you don't get much from generic large language models is it just says, I don't know, because it looks through its documents and doesn't find a good match for this in the documents here. So even though, you know, if I were to ask this just of ChatGPT, so the same model out here, 3.5 here, and I were to ask the same question, it should give me, make up some answer. It won't say I don't know. So it just, you know, these are the courses that are required at some college somewhere. I might even if I was more specific of a history major at the college. Does it know this, I wonder? I haven't tried this. So again, it says it's better. It says I don't have access to that specific information at St. Scholastica. But again, if I just ask the question without that, it gives me an answer. But again, with a RAG system, it will more closely say things like I don't know for this. So you can try this out. Again, you loaded up probably the student catalog or the handbook, or I think the student employee handbook was there too. You loaded in one of these, ask questions of this that it can answer here. So let's see. And try that out. Oh, I don't even ask you a question for that. Sorry. I thought I asked you a question. I asked you about this, I guess. Now, we could do this every time, but every time we have to load up our documents into this, we have to split our documents up, we have to encode all of our documents, and then we have to put them in a vector store. And you have to do that every time you want to ask a question. So that's not very efficient. So someone said, there's ways to make money out of this. So someone said, I'm going to start a company and let you store this information, this vector store out in my company's server there. And you can pay me some money to do that there. And so there's a number of people doing this. The video uses some place called Pinecone. Pinecone. Yeah. So if I go look at Pinecone, this is one of these big investment things. So I search for Pinecone and I get DataStax and Rockset and Elastic are paying a lot of money to get their results above Pinecone because they're competitors for Pinecone. So, but here's Pinecone here, talks about setting this up here, and talks about their, again, relative new company. Let's see, if I scroll down here, they should tell us of their investments here. They just got millions of dollars in startup invested, here. I don't see that here. But again, they're one of these new companies here. Now, the video will walk you through creating a login and setting things up here. I've done that for you, but if you ever want to do this yourself, the video walks you through this here. You have to log in or sign in here. And again, I'm just using my Google login for this. And you don't have to do this for things, but I've logged in. One of the reasons is that, again, I didn't want to have you all have to create Pinecone accounts just for this one little thing. So I created one. But then I didn't want you to upload documents because I've already uploaded documents and I don't want more documents uploaded into this one thing. So in Pinecone, we created an index. So I just created this index called CIS 3115 RAG for this. And when I do that, I had to set the dimension. So I set the dimensions to, and one of the options was OpenAI's 1536. So that's the dimensions. I had to select a region, and by default, it selected Iowa as the closest data center for this here, and sets this up. And then I can load in my document. So here, we set up Pinecone. I've already done this. Oh, I need an API also. So in Pinecone, there you get an API where this is my code so that only I or us can access this stuff here. So that's my API key put in here. And we're saving it to environment. And here's my index name. That's the index I've created here for this. And then this code will go through all the embeddings and split up or parts of documents I have and push them all into this Pinecone repository. So I've done that here. So that's why you can see student handbook, each section of the student, there's a bunch of sections of the student handbook here. I've also got the catalog in here also, I believe, here. So this is already pushed in here and it remembers it. So every time I don't have to do all this other stuff, I can just say, use this Pinecone repository or vector database. So that's why this code is pre-done for you. You don't have to run this. So now how do we use it? Since that's already created, again, we just specify the index name and our key. And we say, give me a Pinecone vector store from an existing index. there, and it goes out and gets that. And then I can ask it a question for this here, or so I'm going to run that. And then I can put this in my chain. So I can use my pinecone retriever. And if you remember our pictures, I thought we had a picture here. This is our vector store. This is now pinecone on the cloud. And this is our retriever. And so our question goes to that. It goes out here, gets the related documents, bring them back, and then we're send to our prompt is our question and our context. And we send that to our model. So here's my question. Can students drink alcohol in their dorm rooms? I'm going to run that. And it should tell me, based on the context provided, students, here. And again, so that's searching all the documents in Pinecone. So it should, I think it has the course catalog here. So let's try. How many credits does a student need for a bachelor's degree? I think that's in the catalog. Student needs a total of 128 credits for a bachelor's degree. That's right. Well, it's kind of out of date because we've just increased it to 120. And that's in the upcoming catalog, but not in the current catalog. So I have the current catalog. But next year, I can simply update this with the new catalog here, and then that would be better. So you can try this out on a couple things. You'll see it does hopefully a fairly good job, but it will fail on a number of things, particularly on lists and bullet items and stuff that are in the catalog. So like if I ask it what courses are required for a history major, it should come up with a list of courses. Oops. And again, what it does is it goes out there, it embeds this question and goes to the vector store here, which has all these embeddings, finds the embeddings that are closest, a cosine similarity closest to my question. So again, I'm asking for history majors and courses required. So to look any place in the catalog where it's talking about history major courses required, those would be close. It should find the corresponding segments here and return those. It'll send those to ChatGPT or OpenAI along with my query, and it should get me a result here for this. And the result is history 3206, and it just returns one course, which is required for the history major, but it doesn't list all the courses. So it doesn't do that very well right now. And I had some trouble encoding the catalog, the way the PDF was set up. So it might be related to how I had to convert the catalog to a text file here. So I'm not quite sure. Because I notice sometimes when we see this, there's a fair amount of what I call noise, extra characters in this text here. So I don't know how it's encoding like bullet items and stuff like that. So I'm a little like this sort of stuff's got me a little worried. If I were doing this for real, I'd be working to clean up my text prompts before I sent it in, before I put it in here. Okay. This talks about steps for getting your Pinecone API key set up and index. And again, that's just going here, creating an account, once you create an account, you get an API key, and then you can go to indexes and just create an index. Here, when you create an index, you specify the region. Iowa default. I want to stay into the free plan. Here it has what's, what metrics, and we're going to use cosine similarity. Who uses dot product these days? I mean, come on. So really sad to tell linear algebra jokes in this class when no one gets linear algebra jokes. So that's okay. So, and again, we did, and then we have to specify where's the dimensions here and we can actually set this up by model, and we can just pick the OpenAI model here and use that. Okay. Questions on this? How'd this go today? So. Again, RAG's really big out there as far as learning management systems, jobs, and stuff like that. So, and you can kind of see lots of companies are using this in different ways. So it's just a basic intro. Well, Thursday we'll give you time to work on the project for this week. The project is going to be very open-ended in that you're going to design kind of an experiment or something you want to try out with large language models. Anything we've covered in the last few weeks, prompt engineering, agents or RAG, set up any of those models and then try some experiment on them to see how it works, because it kind of gives you prep for the whole final project, which I'll release in the final project the same way, except the final project, you can take any model we've done in class and do an experiment and run an experiment and write up a paper about it. So it's just a little preview. If you remember when we did CNN, at one point we let you I had a CNN there and you could try different things, make a hypothesis and do that. So I'll post that by Thursday, and Thursday we'll work through that. So, okay.